Hey everybody, this is a thermal physics lecture on states of matter, phase changes, latent heat, and heating curves. It assumes that you have already studied specific heat capacity, heat, and temperature. Here's an overview of what we're going to cover. First, states of matter and phase changes, then how that's related to the potential energy of molecules and the kinetic energy using a PhET sim. We're going to talk about latent heat capacity and heating curves. So let's start by identifying our three most common states of matter. Those are solid, liquid, and gas. And we're going to talk about this from a molecular point of view. In a solid, the molecules are packed closely together because there are strong physical bonds holding the molecules in position relative to the other molecules, which means the molecules can't move relative to each other, so they have a fixed volume and a fixed shape. In a liquid, the molecules are still pretty closely packed together, but the physical bonds can break and reform, and so the molecules can kind of flow around one another. The volume of a liquid is generally quite fixed, but a liquid will take the shape of its container because the molecules can move around relative to each other. And in a gas, the molecules are very far away from each other, and there are practically no forces or physical bonds between the molecules. Gases will fill the volume and shape of the container that they are in. Standard three states of matter. You also need to know the names for the different state changes or phase changes. Solid to liquid is melting. Liquid to solid is freezing. Liquid to gas is called boiling. And gas to liquid is called condensation. Now there are a few other phase changes like sublimation, which is solid to gas, but we're not going to worry about that today. There is one other important phase change from liquid to gas called evaporation. And I'll talk about that in the PhET sim. Most of these phase changes occur at a very specific temperature, but evaporation can happen at any temperature. So let's take a look at these at a molecular level. This is a PhET sim on states of matter. We're going to look at phase changes. So let's just take a look at argon in the different states. This is solid argon. The molecules are moving, they're vibrating, but they're fixed relative to one another. If I add heat, I'm going to increase the temperature and they will start vibrating faster, but they still stay fixed relative to each other. Now if I continue to add heat, eventually they will start moving around each other, start sliding, and we'll get into liquid form. This is liquid argon. The molecules pretty much stick together, closely together, but they kind of roll around each other. Now, their position relative to each other is about fixed, but they're moving a little bit faster. Notice that there are also these kind of random molecules that escape this big liquid blob. And those would be gas molecules. And that's what evaporation is, when an individual molecule just gains enough energy to escape that liquid, or even that solid. If I continue to add energy, I can heat this argon to boiling, and it will enter the gas phase. So this is the gas phase. The molecules are pretty far away from one another. They're pretty much all acting almost entirely solo. Notice there are some weak physical bonds that form every once in a while and reform. That's actually not going to happen very often for a real gas, but it does happen for the purposes of this sim. The vast majority of molecules are not bound to anything else, or they're only bound to one or two other molecules. So those are our three states or phases of matter. Let's go back to the PowerPoint. Okay, so let's talk about thermal and internal energy. So when we add heat to a substance, we've already mentioned that it can increase the kinetic energy of our substance. And kinetic energy, at least the linear kinetic energy, is related to the temperature of our substance. So we increase the speed of the molecules, but they stay about the same distance apart. The other thing that happens when we add heat is we can increase the potential energy. And this is what occurs during a phase change. During a phase change, the physical bonds that hold those molecules in place are broken. Another way you can think about it is we're separating the molecules. They're moving farther away from one another across these attractive forces. Therefore, we've increased the potential energy. The same as if you lift something up in a gravitational field. You separate the Earth and the object, you're increasing the potential energy because there's that attractive force. What's interesting is during a phase change, the average speed stays constant. We're just increasing the average distance of the molecules. We're also going to define this new term, internal energy. The variable is a capital U. Internal energy is the total kinetic plus potential energy of the molecules in a substance. So we can think of that as the total energy required to heat an object from, or to heat a substance from absolute zero to its current temperature and phase. Or if we have a substance, how much heat would we have to remove to cool it down to absolute zero? And there's a little representation of internal energy here. We have the kinetic energy of the molecules and the potential energy of the molecules, which is related to the molecular attractive forces, or the physical bonds. So next up is specific latent heat. Heat can change the temperature or the phase of a substance, but it turns out, luckily, that it does not change both at the same time. It only changes one or another. During a temperature change, the kinetic energy increases, and we use Q equals mc delta T. During a phase change, well, first of all, a phase change will occur at a specific temperature called the boiling point, freezing point, melting point, except for evaporation, which, as I mentioned, can occur at all temperatures. And during boiling, melting, or freezing, the heat added changes the phase, not the temperature. So because we can't measure that temperature change, that heat is hidden, so that heat is called the latent heat of a substance. Our equation for latent heat, or for phase changes, is Q equals mL. Now, for most substances, there are going to be two different L values. Actually, let me define L. Let me define these variables. Q is the heat that you add to a substance or take away. M is the mass. And L is the specific latent heat of a substance. There are two specific latent heats. There's one for vaporization, which is the phase change between liquid and gas, and one for fusion, the phase change between solid and liquid. And these specific latent heat values are just constants of the substance, and they're going to be different for each substance and phase change. The specific latent heat tells us how much energy is required to boil or to melt or to freeze 1 kilogram or 1 gram, depending on units, of the substance. So its specific latent heat is measured in joules per kilogram, kilojoules per kilogram, joules per gram, etc. Again, there are two different latent heats per substance. There's going to be the latent heat of vaporization for liquid to gas, or vice versa, and the specific latent heat of fusion for solid to liquid or liquid to solid. So let's do one latent heat problem. 225 grams of steam is cooled to 100 degrees Celsius. How much heat must be removed to condense it into liquid water? The latent heat of vaporization of water is 2,265 joules per gram. Well, we know that Q equals mL. We know that the steam is at 100 degrees Celsius, which is the boiling point of steam. So if we remove any more heat, that steam is going to start condensing into water. If we want to fully condense it, we're going to have to condense the entire mass of the water. So really we just need to plug in our numbers. Q equals M225 grams times L, 2265 joules per gram. Now, you want to be careful about units here. You need to make sure that your mass units cancel, grams over grams, and we're left with units of joules. 2225 times 2265 is equal to a very large number, 5.09, actually 5.10 times 10 to the 5 joules. Now, one little last thing we want to note about this, the heat for the steam is going to be negative because heat is removed from our substance. So keep that in mind. It really should be negative 5.10 times 10 to the 5 joules. That does not come out of the equation. You just have to know that because we are removing heat. So that actually covers everything that we need if we want to figure out how heat affects a substance. This slide shows a heating curve for a substance, and it's going to be pretty much the same type of heating curve for every substance. We have our three states of matter, solid, liquid, and gas, represented by these sloped lines. And they'll all have different slopes, and they'll all have different widths, but they are sloped lines. If we're dealing with a constant phase, we're going to use Q equals mc delta T. We also have these plateaus, which represent boiling or freezing or melting, a phase change. And they're going to occur at our boiling points and freezing points. So if, for example, I said that I had some ice water, or some ice, let's say, at negative 5 degrees, and I wanted to heat it to a 15-degree liquid. Well, I know that ice is a solid form, so we're starting out here, and I want to heat it to liquid at 15 degrees. I know that 15 degrees is above the freezing point of water, so it's going to be somewhere in this liquid form. If I wanted to figure out how much heat was required, I could take a look at this heat temperature curve. I know that more heat is to the right, so I'm going to go along this line to heat it up to the freezing point or the melting point. I'm going to go along this line to fully melt it, and then I'm going to go along this line to heat it up again. And so there are going to be 1, 2, 3 different parts, 3 different equations I'm going to have to use to figure out the total heat. And all we're going to do is add up the total heat here to find the total heat. During the first phase, during a solid, we'll use Q equals mc for ice, delta T for that ice. During our melting, we'll use Q equals ml, and since it's melting, we'll use the latent heat of fusion. And during the third phase, we'll use Q equals mc of the water, delta T of the water. Let's go back. And to find the total heat, that's just going to be Q1 plus Q2 plus Q3. So for any problem involving changes of phase, we're actually going to use this heating curve. We can just sketch it out and diagram out how we're going to organize our heats and then add them up or set up our equations and solve. There will be some problems in the next lecture that go more in depth with examples of these heating curves and how to use latent heat. That's all for now. Thank you. Bye.